Bismillahirrahmanirrahim. Hi all, welcome to Structure Analysis Essential. In this lecture, we will discuss the combined stresses produced by the axial and flexural type of loading. So, as in the previous lecture, we have talked about different type of stresses. Uh, Mainly, there are four different, basically two type of stresses. There is either normal stresses or shear stresses. The journal overview. So the normal stress includes the compressive tensile stresses, flexural stresses, and shear stresses due to shear forces. And the shear stresses may be produced due to the torsion or the twisting movement. This is the bending movement. This one, the bending movement. One is the twisting movement. As we have discussed in the previous lecture, the difference of the twisting and the bending movement. So, first we will deal these type of stresses separately, then we will combine them. For example, you have a beam of length L and it has some cross section having B and H. So when the load is applied at the centroid in the center of the section, so the stresses produced in this beam will be P by A. Either it is minus P by A or plus P by A. If the force is compressive force, then the stresses will be produced. I am assuming compressive force as a negative. You may consider it as a positive. So, if you consider compressive stresses as negative, then the tensile stresses will be positive. So, this type, and this is the stress profile. Stress profile. The whole section and each fibers will be under same state of stress, and that's same magnitude of the stress, and that is equal to minus P by A along the height of the section. So for P by A, your load must be applied at the center of the section. And for example, if another beam considered and there is only pure bending case, so remember this, there is no shear forces in pure bending case. In pure bending case, so no shear forces will produced in this type of, and there is constant movement at each section, and that value is M. And we will also discuss this in basic structure analysis course, that how we can draw the shear force and bending moment. Basically, it's if it is a beam of having this M and this, you can draw the shear force is 0 and the bending moment will be a constant bending straight line 0-degree curve. So this is the shear force and bending moment diagram. Basically, no shear force diagram. And if the bending is beam is subjected to pure bending, this type of stress is known as the flexural stresses, and its value is plus minus my by I. So this is the m. Y is the, if this is the cross section of the beam, y is the distance from the centroid. For example, you are interested here to find the stress here, here, and here. When you go to the full height, half height means y is equal to h by 2. You can also, in some books, you will also see a formula like mc by I. Y is any fiber distance, while c is the maximum distance from center to the top fibers or bottom fibers. So in this case, the stresses produced due to the bending moment will be my by a, and due to the axial force, either it is compressions or tension, the forces will produce by p by a. Now, uh, the, at the top, if we look this one, so combined stresses, we will combine this in the next slide. So let me clear some space. So this beam will bend like this. So the upper fibers are in compression and the bottoms are in tension. So the stress profile of this will be like this. So if you are taking this compression as negative, so similarly this value, which will be equal to my by I, that will be negative, and this will be positive my by I. So, and this neutral axis and the centroidal axis will coincide in pure bending case. But when we combine this stress profile and this stress profile, as you can see, this, so it may be greater, and one ordinate will be greater and one ordinate will be small. So the center will not be centroidal and neutral axis will not be coincide in such case. So after this, what is the scenario in beams and columns? For example, when a beam of length, total length L, and the half distance are, you can say L by 2 and L by 2, and there is a load P is subjected. Now here it is, if you make its component, that will be equal to P cos theta, and this will be equal to P sine theta, this vertical load, and this horizontal load is P cos theta. So now this force is acting in this direction at the top of the fiber. But we see in this here, this type of P by A stresses is produced when the load is applied at the center of the section. So you must transfer this force, if I say it is F1 and this is F2, so this F1 you can apply this in the both direction. So we have nothing, we have not changed the problem basically. So this is F1 and F1. We have applied each other. This may cancel each other and we have not changed the problem basically. So now this force and this force, definitely if we are shifting this from the top to the center, if this is h, so definitely this distance will be h by 2. So you are here will also basically, if you convert this here, so there will be a load of F2. Now this inclined load will finish and this will produce a couple of this one along with the axial force. So this force will remain here, and this force and this will produce a couple, and this F2 will also be here. And so now due to the axial force, and you can draw the by using analysis, basic structure analysis, you can draw its shear force and bending moment diagram. So it may be like this one, because there is a point movement, either this point will go up or down, then this will be a bending moment diagram. So at any section you can use the value of m. If you want to interest it 1 feet or 2 feet from here, the stresses at this sections, so definitely this p is acting along whole beam. So this is minus p by a and plus m y by I. As you know cross sections, I you can calculate from the cross sections area, from the cross sections. Y you can also use y, and m at any section. So this is the variation of the bending moment diagram along the length of the beam. So this is the combined stress in the beams. So combined stresses in the column, if the load is subjected to, if the load is applied at some eccentricity from the centroidal axis. So this eccentricity may be in two cases. It may be biaxial columns or uniaxial column. For example, if this is the cross sections of this column, if you see this column from the top, you will see this one. If this P is, if this load P is applied on one axis at some eccentricity E along the x-axis only, and this is the case of the uniaxial case. If the mm, load is applied between x and y axis, this is the load P, which is this one. But in the first ordinate or anywhere here, here, or here, so this will bend the column along this directions and along this direction. But in this case, we will only, this is the M. And this is M. This is the MY. This is because this is the this will produce the movement along y-axis. When you multiply this phi, you strike your pen on the paper, this point, this will rotate this section about this axis. So this is my. And its value is p into e distance. If this is y distance and this is x distance, so you can use this type of. So this is the general considerations. So for example, in such cases, for example, the if a beam is subjected to UDL and this type of stresses P, so the stress produced due to the P is this one, minus P by A, and this is minus P by A, if this is the centroidal axis. If this is centroidal axis. And with the UDL will bend like this. So upper is compression, bottom is tension. So if we add this one with this thing, so this is plus my by I, and this is minus my by I. So the net minus and minus will be plus. This will go here, and this one. In this case, the neutral axis, this is the neutral axis, and this is the centroidal axis. So the neutral axis will shift down. You can also calculate this distance, because you know this minus p by a plus my by I. Let's suppose you get an answer B, and this is minus p by a and minus my by I, and you get an answer A. So you know this A is A. Consider this distance from bottom, this is y, and you know this height, this is basically the beam depth d. So by using the similarity of triangle, you can use, so a, this distance is a and this distance is b. So a by d minus y. So from total d you will subtract this one minus y. So this will from here, from this here to here, you will get this distance. This is d minus y, and b by b by y. So now you have one equation and you have only one unknown, that is y. So that's in this you can location of neutral axis. Axis. This is the location of the neutral axis. So thanks for watching my video. Wish you best of luck.